You start with the best tools available. You download a massive, state-of-the-art embedding model and carefully load it into your environment. On standard benchmarks, it performs beautifully. It reads general English, groups common synonyms, and maps basic concepts with perfect geometric precision. But then you flood the system with your actual production data. Proprietary legal contracts, internal acronyms, and operational logs hit all at once. The system immediately struggles. Because the model doesn't understand your highly specialized jargon, a search for a critical technical spec pulls in the wrong documents, conceptually adjacent but operationally useless. Think of this off-the-shelf model as a brilliant generalist librarian. They know exactly where the history section is, but if you ask them to locate a highly specific corporate subclause hidden inside a dense engineering database, they are going to hand you a generic manual instead. You cannot prompt your way out of this problem. If the model inherently misinterprets the vocabulary, the underlying geometry of its vector space must be entirely rebuilt. The first step to rebuilding that geometry is domain adaptation. You fine-tune the embeddings using your own data, so the model learns exactly what your industry-specific acronyms and terms actually mean. As the training progresses, the vector space reorganizes. The model begins pulling those specialized terms away from the generic vocabulary, locking them into tightly bound, distinct clusters that match your company's actual logic. Yet, resolving the jargon gap introduces a new problem. The system now makes subtle precision errors. A query will return documents that share the exact keywords you searched for, but mean the complete opposite thing. If you try to correct this by training the model with standard, random negative examples, it won't work. Showing the model a recipe for cake to prove it's not a legal contract is too easy. It learns nothing about nuance. To fix this, you have to introduce hard negatives. These are data points that look statistically identical on the surface, sharing nearly all the same words, but have vastly different semantic meanings. A standard negative is like handing a nightclub bouncer a library card to get in. The rejection is obvious. A hard negative is a nearly flawless counterfeit ID. By forcing the model to repeatedly distinguish between those near-identical counterfeits and the real thing, it learns the microscopic semantic details that separate true relevance from statistical noise. Accuracy is secured, but the infrastructure is now buckling. Loading millions of these high-dimensional, highly precise vectors into memory requires massive bandwidth, actively crashing the database under real traffic. To keep the system online, you apply index quantization. This is a mathematical compression technique designed to drastically reduce the data size of the vectors. Quantization strips away excess precision, shrinking each coordinate's footprint. Crucially, while the grid becomes blockier, the directional arrows remain pointing the exact same way. You trade a microscopic fraction of recall accuracy for a massive, necessary gain in retrieval speed and stability. The final physical limit is the long document problem. You simply cannot compress 50 pages of dense PDF text into a single solitary vector and expect it to retain any useful nuance. Instead, you deploy chunking strategies. You break those large files into overlapping vector representations, ensuring the retriever doesn't skip over a vital piece of evidence buried on page 40. An embedding model's geometric accuracy means nothing if its physical footprint and chunking architecture prevent it from surviving the demands of real-world traffic. Once deployed, you immediately establish strict similarity thresholds. If a document's vector doesn't land close enough to the query, the system drops it, preventing the language model from attempting to reason over low-confidence, irrelevant garbage. But the work does not end at launch. Over time, users will ask completely new questions, and corporate language naturally evolves. This introduces retrieval drift. Without intervention, the custom embeddings slowly drift out of alignment with those live queries, and the system's performance steadily degrades. This makes the embedding index a continuously monitored feedback loop, requiring regular evaluation and reindexing, rather than a static database you set and forget. You stop viewing vector space as a fixed map and start treating it as a living, breathing engine that must adapt to its environment. Controlling domain adaptation, mastering hard negatives, and scaling with quantization is what transforms a researcher evaluating lab metrics into an engineer running a production system.